So, very warm welcome, everyone. We host today for the Cosmos Seminar Series Antonio Ferreiro from the University of Utrecht, and he will give a talk about another critical look at inflationary cosmology. Thank you very much for being here today, Antonio. I leave it to you.
Yes, great. Thank you, Sylvia. Thank you for the invitation. Yeah, so I will be talking about a project that we have been working on for some time. I'm doing it in collaboration with Alex Fleuren. And it's basically about a reanalysis of the epistemology of the program of inflation, but focusing especially on, let's say, the transformation that the program had in the last 25 years in the context of lambda CDM cosmology and in precision cosmology. So before I do so, let me just state my position here a bit to that will guide us in the way we have analyzed the program of inflation. So in order to do so, I want to give you this quote, but 1 minute because I cannot read it because I see your pictures in the on the right hand side. Right. Uh, okay. Okay. Now, this is from Lev Landau in the 60s. This was in the context of nuclear physics, of the research of nuclear physics that have was going on at that time. So I will read it. So he said, "It is well known that theoretical physics is at present almost helpless in dealing with the problem of strong interactions. By now, the nullification of the theory is tacitly accepted even by theoretical physicists who profess to dispute it. This is evident from the almost complete disappearance of papers on meson theories, and particularly from Dyson's assertion that the correct theory will not be found in the next 100 years." So you can see here a bit the context of what people, the physicists at that time, thought about nuclear physics. So although there was a lot of progress on experiments, on details and data of nuclear physics, on the theory side, people were less optimistic, and actually the hopes were almost zero, which then obviously after not much than 10 or 15 years, this was completely radically changed because QCD was formulated and quantum chromodynamics and this theory, a full developed quantum theory, was able to explain the nuclear data, and now of course it's a well-established theory within the standard model of particles. So the message I want to extract from this is that, at least in our position here, is that in the case of inflation now, I think the situation is it's analog in the sense that it is extremely difficult to assess whether a framework like inflation will be established as a theory in the future, and in what ways this can happen. And consequently, we cannot easily assess what extra empirical virtues should be considered. So we really have this, let's say, this assumption, and so we want to do like a complementary analysis in comparison to this line of investigation that has been going on. And here I can reference you very nice works that have been doing in that direction of asking what reasons should we have to continue inflation, or what should the next steps be. Our position is actually that inflation should be considered as a kind of starting point to a change of scientific paradigm. This is because basically we have to accept that in cosmology, first, cosmology is already different from many of the methodologies of physics that we have seen so far. But even within cosmology, we have not yet constitute a completely new theory in the realm of cosmology. So all the theories that we have used for understanding cosmological data, they have been already been well accepted and have been studied in other types of systems that are not cosmology. So usually, if we think of it as a new scientific paradigm, usually that comes in hand with new methodologies, and so we feel like better position or a complementary position is to actually critically analyze these new methodologies that are actually arising today, or at least the last decades, and try to do epistemology of inflation, focusing on this kind of parts. So what we will do is in this talk, we focus instead of more like extra empirical approaches or how to establish the theories or so on. We actually want to focus on what I call a system of epistemic activities. This is borrowed from Hasok Chang in the sense that we understand a scientific practice, not like an isolated theory on one hand and the rest on the other, but actually as an intertwined system of theories, modeling, data, and so on. In our case, obviously, the one we will focus is on the project of precision cosmology and lambda CDM. And we want to analyze inflation in this context, and we will focus then on three of those possibilities of scientific practice. So on one hand, it's the traditional way of thinking about inflation. So inflation as a model to provide the initial conditions for lambda CDM. Then I will briefly talk about inflation as a dynamical theory, although some work has been already done in that direction. And then I will propose a maybe new way of thinking about inflation in the context of what is currently the scientific practice, which is inflation as a bridge to new theories. And I will try to argue that actually only the option C, provides a possible epistemic shift for the field in the context of lambda CDM and cosmology. And within this context, I will hopefully try to provide you a good definition of inflation. So I cannot see anything from the chat. So if there's any question, please just ask with voice because I
There
cannot
are
see.
no questions for now. Thank
Okay. Yeah. So let me start with the first approach. So let's say the traditional way of teaching inflation. So in order to do that, let me just give a very, very brief introduction to cosmology and lambda CDM cosmology. So here you can see two pictures of the cosmic microwave background. On the left-hand side, we have the initial picture of the CMB, the original one in the 65 by Penzias and Wilson. Basically, what the detection of this, sorry, the CMB stated was that we have a good confirmation of the Big Bang model in the sense that if we go back in time, we arrive to a phase that is radiation dominated, and we usually think that it has to do with a hot plasma of interacting photons and atoms interacting with each other in thermal equilibrium. And then from that, one can extract the fact that photons will be decoupled, and one then would assume that as CMB is left, and we detect it, so we assume this model is right. And on the right-hand side, you can see a well better picture that, of course, confirmed also the Big Bang model, but actually not only that, but it gave us a very precise measurement of the temperature, and that is important for us, the fact that there are tiny anisotropies of these temperatures spread around the sky of the order 10 to the minus 5. Now, where does inflation appear? Well, inflation appear in between these two stages of the detection of the CMB in the 80s. And the idea here is to add an accelerated de Sitter spacetime prior to the Big Bang. And what we mean by prior to the Big Bang means that it's a phase that happened prior to this hot plasma of interacting photons and atoms, okay? So we are not talking here about previous to the singularity or anything, but just once we assume that there is a hot radiation dominated phase, we add a prior phase that would be this accelerated de Sitter space. And the idea here is that this helps us to understand some fine-tuning issues of the CMB, and in particular the fine-tuning that is why is the CMB so homogeneous on one hand, and why is the space so flat? Okay, but most importantly, and this will be clear, the biggest part for our talk, is that it provides a mechanism using quantum physics to the origin of these tiny anisotropies that then Kobe measured. Okay, so this is this phase, but now of course we are interested in lambda CDM. So comparing now COBE with WMAP, which was that detected the CMB during the early 2000s. Um, the transition obviously was in precision. We got more precise data, but there was a clear change. People calls it even a revolution of the cosmology because a new research program was constituted. And the research program has to do with the convergence of what is called the lambda CDM model and precision cosmology. So we want to ask the question, what is the role of inflation now within this new program of lambda CDM? So I have here a sketch of how I see the research program of lambda CDM plus precision cosmology. So here I'm taking into account not only mathematical models, theories, but also data and observations. So we can very sketchy divide it into three parts. So on one hand, we have theories where I include also theoretical models. These are the theories that we need to understand cosmology. So, and usually there are standard theories that are well known: general relativity, hydrodynamics, could be also thermodynamics, atomic physics, so on and so forth. Then we have obviously data. So I gave you here some examples. So for some theoretical models that we need are isotropic and homogeneous spacetimes. We need also to know something about how baryons and photons interact, as I said before, to understand this CMB. Data can be many. Usually, the CMB has to do with temperature variations across the sky. And then also important, we have phenomenological models. And by phenomenological models, I mean models that don't, let's say, they are not solutions of a given theory, but they have to be, let's say, added by hand. And the typical three that appear in our context are dark energy, dark matter, and the primordial power spectrum. Um, so in terms of what lambda CDM means, the lambda CDM model, it would be the combination of theories and theoretical models and these phenomenological models. And the idea is that we have a model that has these two components, and it leaves six parameters free that then, using the data, are fixed to a precise value. And in this picture, you can see the table of the Planck data. And then you can see by the arrow bars what we mean by precision cosmology, and it's the fact that these values can be measured with a very good precision, similar to other laboratory experiments. Okay, so let me give you a more detailed, a specific example of this. So in the left-hand side, you can see the plot of the temperature variations of the cosmic microwave background. And there you can clearly see what this lambda CDM precision cosmology convergence is about. So we have the dots, the black dots, which are data points, which at least if we forget a bit about the large scale, it has very low error bars. So we're talking about precision cosmology. And we have the curve, the gray, which is the model of lambda CDM, and the fit of the two is very good. And so more specifically, if we want to understand this, we have to compute what is called the angular power spectrum. And this angular power spectrum, it has three components, which are important for us. So on the first one is what's called the primordial power scalar spectrum. So basically, these are the initial conditions that we want to plug in to compute the temperature anisotropies. The way of proceeding is just basically to model this. So we have what is called the almost Harrison-Saldovic model. As you can see, it's relatively simple to model this. Then we have the transfer function, this sigma function. And this transfer function includes all the physics from the initial conditions up to the formation of the CMB. So all this physics of the plasma of photons and baryons, and from the CMB to today, which means all the expansion that happens in the late time universe. Um, and then also we have them to model in reionization, but it's not so important for this discussion. So what I want to stress out in terms of the role inflation plays, which is important for us, is the difference between the physics of the transfer function and how we model the primordial power scalar spectrum for the following reason. So as I said before, we have these six parameters that are free in our model, and they enter the angular power spectrum. Okay, we can use the angular power spectrum to then extract and fit these six parameters, but they do so in different ways. So it's not the same way how these parameters are introduced. So, for example, omega B and omega C, so the density of baryons and the density of cold dark matter, enter the dynamics of baryonic acoustic oscillations required to model the transfer function. Now, these baryonic acoustic oscillations, how you can see the picture, cannot be modeled just by focusing on a specific, let's say, a mathematical model like the Harrison-Seldovic model, but actually require theories, require general relativity, hydrodynamics, and also requires many types of idealizations, approximations, so really it's a physical account of the dynamics of baryonic acoustic oscillations. And so the way dark matter and the way the baryonic matter appears in this physics has to do with takes more into account the dynamical, let's say, behavior of the physics to model the transfer function. Okay, so to model the transfer function, we require really a dynamical understanding of these baryonic acoustic oscillations, and the role of dark matter and baryonic matter have a role in this. But on the other hand, to model the primordial power spectrum where AS and NS enter, which is the amplitude and the spectral index of the primordial power spectrum, this is just a formal model. As you can see there, this is enough to explain the CMB. And then the thing is that inflation, as it is understood now today, provides the mechanism for only for this power spectrum. So the way inflation enters into the picture is only through the way this primordial power spectrum is modeled. So it gives you this almost Harrison-Soldovic power spectrum. So as you can see, I hope to make a bit clear that there is a difference in, for instance, how omega B or omega C appear and how the parameters that are related to inflation appear in the model. So let me just extract some conclusions at this point from this. So we can see that we have three different phenomenological models, which we would like to understand the dynamics about from dark energy, dark matter, and primordial power spectrum. But one has to be careful because at least the epistemic role they play in lambda CDM is different. So, for instance, dark matter, as I have said, it participates in the baryonic acoustic oscillation and in dynamics, and basically from then one can extract at least some properties that dark matter should obey. For instance, that it appears to source the gravitational expansion as a form of matter, but on the other hand, it doesn't interact with the baryonic and the photon fields. So from these two ideas, one can already give a sense of what we mean by dark matter. But in contrast, for the primordial power spectrum, which is related to inflation, only with the primordial power spectrum, because there is no dynamics associated to it, we cannot from that provide any property to the inflation field. So in this sense, inflation is added externally to the lambda CDM, but the key point here to understand is that lambda CDM can work as a research program independent of inflation. Okay, so in this sense, dark matter and dark energy, they have already, let's say, passed the test to have an epistemic role in the lambda CDM, but inflation has not. Okay. So I usually compare this actually to another more forgotten aspect of cosmology, which is baryogenesis. So we know that the energy density of matter is not zero, but actually theoretically one would think it is zero because there is at least theoretically the symmetry between matter and antimatter. So to understand why it's different, one needs to introduce some mechanism, which is usually called baryogenesis, to explain this. And there are many proposals, but again, this mechanism, as it's very similar to inflation, does not play a role in lambda CTM. So actually, one can put by hand that the omega matter is different to zero, and one can proceed in any case. So in this sense, inflation has more to, let's say, epistemically more similar to baryogenesis than actually to dark matter or dark energy. But I will briefly show is that inflation, in this sense, I mean, it has become obviously a bigger program than baryogenesis because it has had a progress from precision cosmology in the last decades, whereas baryogenesis, in this sense, has been more stacked because the only parameter that enters baryogenesis is omega matter, and omega matter is already fixed by data. So from the more sorry, precision cosmology point of view, uh, now focusing on inflation and how inflation provides this primordial power spectrum. So if inflation happened, then we would have, you can see on the left-hand side, three consequences. On one hand, we have an almost scale invariant power spectrum, which I already showed, but we also have a tensor power spectrum. So inflation naturally also produce tensor perturbations, and in principle, it should also produce what is called tiny non-Gaussianities, which basically has to do with also with the distribution of these anisotropies that go beyond the what is called the Gaussian power spectrum. Um, and so if we now check the data, so the scalar index has been measured to be almost one, but not one. That has been done for with high precision. And inflation tells you that it should be different to one because inflation needs to end, and this ending forces you to have a different value. Also, the tensor perturbations have not been measured yet, but they have been very good constraints, and during the last decades, the constraints have been higher and higher. And so the hope is that eventually this can we have the techniques available and to reduce this even more, the upper bound, and to either find tensor perturbations, or if we don't find it, put very tight constraints on it. And finally, about non-Gaussianities, of course, you can see that the error bars are very big. I mean, obviously, it's not so constrained as tensor perturbations, but there is also hope, and the technology is progressively developing to arrive to enough precision to say we have measured or not non-Gaussianities. And they, of course, are very related with inflation. But for our purposes, the progress here has been on the side to say that since we measure non-Gaussianity, we don't measure non-Gaussianities. They are very, very small, and tensor perturbations we have also not measured, but we have constraints. Then this allows us to choose from all the possible models of inflation the simplest ones, which are what it's called the single canonical slow-roll scalar fields. Different several properties of this. And then I put here basically the picture of how this goes. So we have a scalar field and a potential. And during inflation, the scalar field moves straight. And then when the inflation finishes, it goes down to the potential and starts to oscillate. Um, and this produces a de Sitter space, at least at the beginning. And then the idea is that there are fluctuations of the scalar field, and by quantizing them, one gets these anisotropies. And furthermore, when the sorry, the scalar field starts to oscillate, also by a quantum mechanism, one can show that there is a mechanism to transfer all the energy from the scalar field to the standard model particles, which are the one that we observe today. In this phase is called reheating. So this is the simplest model that works well to fit the data. And the good thing is that there is a straightforward way of connecting the spectral index and the tensor to scalar ratio, ns and r, with the form of the potential. Okay. So what this allows us to do is, as you see in the left-hand side, is to plot different potentials and see if they fit the data with available data of the tensor to scalar ratio and the spectral index. And you can see there that already in 2018, many models were disfavored. So, this already feels in some way like kind of progress. But of course, and most importantly, you can see on the right-hand side that it's true that some models were disfavored, but more models have been actually produced, and one can analyze them, and many of them are favorite or weakly favorite, and one can count them in almost more than 100 models available, so different potentials. And this I'm talking even in the simplest models, which are favored by data. One can even make them more complicated, and of course this goes even worse. So of course this is there, and this is there on the determination problem. This has been analyzed by recently. how to properly maybe classify them. I will not go too much into detail. Um, the expectations that okay, how could this be better in the future, they seem, let's say, relatively promising, in the sense that in principle we could detect tensor perturbations. So here's a plot on how to get smaller and smaller bounds on the tensor to scalar ratio. Let's say the green side will be what's called achievable in the next decade, although this plot needs to be reformulated because it takes into account that there was one experiment, the CMBS4, that unfortunately was cancelled. So one would have to reanalyze if this is still possible to reduce the constraints so much. And on the right-hand side, you see the possibility of detecting non-Gaussianities. They are also not very clear if it will be possible, because basically the biggest promise was against CMBS4, which was cancelled. And then basically the role relies not on the CMB part, but actually on large-scale structure. And the problem there is that we need to not only experimentally be precise, but actually theoretically be precise, in the sense to compute these non-Gaussianities, and it's way more difficult than the CMB because of non-linearities. So there is hope, but it's still a difficult path. Now, actually, for our discussion, the most important thing here is that even though this could be observed, they don't really change the epistemological role that inflation plays. Because on one hand, it will not solve the determination problem. So in any case, whatever we detect, there can always be a model of inflation that fit the data. And furthermore, the role of inflation playing this, let's say, external sourcing of the primordial power spectrum will still be the same. We won't have any different role for inflation in this sense. So as you can see in this picture, I put the arrows like broader, so bigger. So of course we could have better reasons to think inflation is a good program, but it still has this external appendix to this, because basically both non-Gaussianities and tensor perturbations, they are still encoded in initial conditions. So again, to model them, we would not require inflation, but actually require just mathematical models like we did with the Harrison-Seldovic power spectrum. So okay, so this is from the first role. Now there is a second way of thinking about inflation. I think I will have to go a bit faster here, which is, of course, the hope that was initially thought that, okay, this is inflation is similar to particle physics, so we have a lot of data, and now we want to really get there and obtain a full dynamical theory of inflation in a similar way of we did with quantum chromodynamics and the example of nuclear physics. And I will briefly say something of at least how this is people think this could be achieved. So to try to give a theoretical full account of inflation, one in the minimal setup, so the minimal ingredients we need is at least to have two theories. Okay, I mean, ideally we want to have only one unified theory that would explain inflation, but one could also think of just two theories. So on one hand, we would like to have one theory that tells us something about how the scalar field and potential are. So they provide us the given scalar field and potential. And on the other hand, we want a theory that is able to quantize the scalar field and most importantly, to tell us how these quantum fields that produce the anisotropies are classicalized. Okay, so let me just briefly explain these two ingredients, these two possible theories. So the first theory that provides us the scalar field and potentials. This can be done, at least how we think it, in three ways. Sorry, sorry, I need to. So the first option is to add by hand a scalar field and a potential. So okay, like we do in, let's say, in particle physics, we think, well, we are measuring a scalar field, so let us just add it to the standard model and hope for the best. Now, of course, the problem is on determination. As I have explained, there are many ways of adding a scalar field and a potential, and if you don't have enough theoretical background to say which one of those the correct is, then you cannot add it by hand. One hope was that effective field theory would, let's say, help us with that. But as Kowaliński and Menk have shown, argue very, very nicely, this has very obstacles that are not clear how effective field theory would provide that. A second option is to modify already existing theories. So we have seen that for the lambda CDM, we need general relativity, atomic physics, and so on. But we can already modify them. And I give very briefly here two options. Modify gravity. So one can think, for instance, an approach that I particularly like is to say, well, we know Einstein's theory is not perturbative or normalizable. So let us find, are there theories gravitationally that are perturbative or normalizable? And the answer is yes. And they are what is called quadratic gravity. And quadratic gravity, in principle, can propose you an inflationary model, which is Starobinsky inflation. So that seems a promising path. Also, the other option is to modify matter. So, for instance, take the Higgs field, which is the only scalar field that we know from particle physics, and couple it non-minimally to gravity. And that can also be an option. And obviously, the third option would be to add completely new degrees of freedom, so add a completely new theory. And then the biggest candidate on the map right now is string theory. Actually, there is a full field called string inflation. Now, the problem that I see personally with string inflation is that it doesn't propose you one potential, it proposes you many potentials. And it has to do with the fact that, of course, string theory has not yet a unique theory that we can control. And therefore, although it serves, let's say, a motivation to different models for using different mechanisms to handle strings. Of course, they just play with this on the determination problem, and it seems difficult to see which one is the correct one. So because of time, let me just briefly say something about the other theory. So in many textbooks, it seems to be like it's transparent how to quantize the scalar field and then to go to the classical classicalization of it. But people during the last year especially, they have reanalyzed this issue and say that it's not trivial at all to prove that these quantum fluctuations really classicalize in any meaningful way. And then what one can do is one can add different mechanisms, so decoherence, collapse, and so on. But of course, these are new things that we have not yet understood well, at least from the gravity side. So they are completely outside the realm of general relativity and particle physics. And then, well, one that I preferably like is that actually one can modify the Einstein's equations to save on this. But this is what my point here is that even in this case, the second theory, it's not a theory that we already have in hand, but it needs to also be researched and generalized to really fit the mechanism of inflation. So the point to make here is that there are good avenues of research programs that have to do with formalizing a theory for inflation. But the point I want to make is that actually instead of having a theory that provides you an explanation of what inflation is, usually the account is the opposite. So one uses inflation as a guiding principle to construct theories. Okay, so usually as a motivation to say, well, I have this need to have a scalar field potential, so this helps me to fit my theory. And for example, in string theory, this can be seen very, very nicely because there's what is called the eta problem when you try to find some scalar potential and then it's okay, how can I? So actually, my point here is that instead of making inflation part of the CDM cosmology and the CDM cosmology, actually it's just helping the theories to be developed. And so in this sense, it doesn't really serve as a purpose to change the epistemic role of cosmic inflation as a cosmic, let's say, element. Um, okay, and then finally, the last role, which I think it's the most promising one, which is to think as an inflation as a bridge to new physics. So because the inflation is actually not some like only like a mechanism that takes place, but actually a completely new phase of the universe. We can think of inflation as some kind of laboratory that could have new impacts in the in measurements because we can actually not try to think about inflation how to measure let's say properties of inflation, but to actually be able to measure things that happen during inflation or inflation or the post-inflationary era, which I said that is what's called reheating. And I propose two ways. There are two ways in the actual research projects, which are again measuring non-Gaussianities and the stochastic gravitational background. So very briefly, non-Gaussianities, as I explained, have to do with the way that the CMB let's say structured, the primordial power spectrum. And there are two interesting research programs that I find interesting. One is loop quantum cosmology, so applying some rules from loop quantum gravity to cosmology. It states that instead of having a big bang, we have a bounce, and this bounce produces non-Gaussianities. And in principle, if we are precise enough, they could be measured. And on the other hand, on the right-hand side, inflation, apart from trying to produce these potentials, it has a very interesting project because it tells you that there are many, many, many degrees of freedom, scalar degrees of freedom of light and heavy particles. And there is an approach that is called the cosmological bootstrap, which is trying to say, well, if these extra degrees of freedom are present during inflation, then what would be, let's say, the outcome of this? And then can we measure this in terms of measuring these non-Gaussianities? And this is similar to like what would be the collider physics approach, where one really doesn't see the dynamics, but one sees just the traces, like the outcomes. And from that one extracts what were the degrees of freedom before. And this is a promising research line. But when I want to highlight this, that this has to do with the fact that inflation exists. So inflation is like, let's say, the base, the laboratory, and on top of that, you put new physics. Okay, and then you try to extract possible predictions from it. And the second option is, again, to measure stochastic gravitational wave background. This has to do with the upcoming detectors of gravitational waves, mostly LISA, which will be hopefully put in function in the next decades. And the idea here is that we measure the stochastic gravitational wave background, and then one can measure very different physics. And actually, one would say, well, can we, for instance, measure the gravitational waves that were produced by inflation with these tensor perturbations? The answer is no. LISA will not be able to measure them because of the frequency band. But what LISA can measure is actually physics that happen during inflation. It has to do with correct, like higher order, let's say, physics beyond inflation. And also, for instance, the reheating epoch. So reheating, this transformation from the scalar field to matter produces gravitational waves, and they can actually be measured by LISA. So these are two examples that show there is a promising research line where one actually assumes inflation, and on top of that puts new physics that can be detected. So then the picture would be something like we started with this role of inflation providing only the modeling for the primordial power spectrum. But if, for instance, we detect the gravitational wave background, and then I put in the data there, the stochastic gravitational wave background, then obviously we need gravitational wave models that come from general relativity and so on. But if we want to source them, if we want to see, okay, what are the possible sources for these gravitational wave models, then one needs new theories. And the way of connecting new theories to gravitational wave models is through inflation. because we need inflation to produce these possible predictions that the new theories could account. So in this sense, the possibility here would be to say that if this is the case, then it is true that inflation could be added to the Lambda CDM model, where we think now as Lambda CDM as a bigger research program that includes these gravitational wave detections. Because in the similar way of how we need dark matter and we need dark energy, in this case, we would actually need inflation to provide gravitational wave models. And in this sense, inflation would have a new epistemic role in this program. So let me then just very briefly say what I think is inflation in this sense, uh, in this last way of thinking about it. So as I said, there was this idea that inflation could be thought of as a theory, as a full theory. But if we take that for now, like on bracket, let's say we have provisional, let's say put this into a project for later, let's say, we can actually then rely on the fact that we can substitute it by models, okay? So instead of thinking what could provide a full theory that provides the scalar field and the potential, we could just think, well, we can model it as a de Sitter space-time that finishes at some point and has a scalar degrees of freedom. And actually, one can show that one can formulate this without even caring about exactly what this potential is about. And they always call this is effective field theory approach, not taking as a full theory, which has some issues, but actually just taking as to be as a model, as a provisional model to formulate in inflation. And then the quantum to classical transition side, again, one will need a theory, but one can actually provisionally substitute it by a model. And this has been proven by Stecker very nicely that one doesn't need to have a full mechanism, because actually one can prove that at least only the measurements of the CMB, only if we have this kind of measurements, one can always substitute quantum correlations by classical correlations. So this is a very beautiful way of thinking about if we don't have better ways of measuring this quantum thing. The CMB doesn't really care if you substitute it by a classical stochastic variable. So this model is completely fine, although one would like to have a theory that provides a full mechanism of this. And then I want to do two comparisons on this so that it feels that it seems like a very strange thing to do, just these two types of models, but actually it's very common to have modelings that are provisional and they work pretty well. So on one hand, the model that serves to substitute the scalar field and the potential can actually, I think, it resembles pretty well with special relativity, in the sense that it is true that we would like, of course, to have a full account of what the scalar field is, in the same way that in special relativity we want to know what clocks are. But in any case, we can use a framework, a mathematical framework, to theorize about this framework without really caring about the details of it, and it gives us a productive outcome. And on the other hand, to do this modeling of the quantum to classical, this is very analog to using mathematical models that are analogous to other models. So, for instance, Harman has shown that there's these development models. In the case of nuclear physics, they have been widely used. For instance, the appearance of color, the notion of color as a analog to the electric charge. And so I felt this is very similar to this case. Um, so to conclude now, as I have said, there are, at least from what we have found, three systems of epistemic activities that include inflation. So on one hand, inflation as a framework to dynamically obtain the power spectrum, let's say the usual way that we have think this for the last decades. Um, if we maintain inflation only in this as this part of this research, inflation cannot really be considered as part of lambda CDM, at least not in the same way as dark energy and dark matter. One can think of inflation as a full dynamical theory, but this can be actually used to assess theoretical research programs rather than cosmic inflation. And finally, inflation as a bridge to new theories. And if we are successful in this program, then inflation would be necessary to be included in the bigger program of precision cosmology. And then actually I give this is the optimistic part, let's say, and then the pessimistic part would be that if there are no detections of non-Gaussianities and gravitational waves, that we think would come from the early universe, then of course this would diminish the problem of inflation, and then we would still be in the role number one, similar to baryogenesis. So it would still be, let's say, a program that is still there. We don't say it's incorrect, but it will, of course, not have so much research power as inflation currently has in the context of cosmology. Yeah, and then I finish here.
Thank you very much, Antonio. You touched so many points.
Yeah,
Of
sorry.
course, you're receiving the the clapping hands from the audience, and we have now the Q&A. So you can just raise your hand through the chat, and if you like, yeah, please, Niels.
Well, I just had a short clarificatory question. At the start, I thought you were saying, when you're talking about Chang, right, and the different epistemic roles, that you were describing three existing practices. And then I thought you were saying, no, you want to advocate a new non-existing epistemic practice or understanding or role. So which of these two is it, or is it the point that the
Yeah,
third
sorry.
one kind of already understands, is there a little bit, but it should be much bigger and better
Yeah,
understood?
yeah. Thank you. I think you're right. Maybe I didn't fully explain this. So at least like let's say from the what the scientific practice is currently about. So what let's say physicists are doing. I think option C is included. So people are really working on this. Uh, my feeling was that this side has not been maybe analyzed from the philosophical side. So understanding the role of inflation in this sense has been a bit omitted and has been mostly focused on A and B. Yeah.
Cool.
Okay, so Federico.
Yeah. Hi. Thank you, Antonio. Mine is kind of a broad question to let you talk a little bit more about mainly the last part of the talk, maybe. Um, because if I understood correctly, your point is that uh, in order to have inflation not as a phenomenological theory as you called, but as have it organically recovered from a theoretical framework, so to
Mhm.
speak, um, we should have something like a theory of quantum gravity or a theory of quantum gravity. Is that correct?
Yes. So I mean, I didn't want to. I wanted to be here as neutral as possible. So I would not force it to be a theory of quantum gravity. It could be any other theory. But you need something else than the theories we have available
Okay.
for now.
So, and how do you see possible proposals? So, among let's say the space of all possible proposals, how do you see eternal inflation? Do you think that's already a theoretical framework that allows you somehow to recover inflation? Or sorry for the question is a little bit out of the scope
Yeah,
of the talk,
I
maybe,
mean,
but
to be honest, I'm not too familiarized with the proposals of eternal inflation.
mm,
I think maybe Alex, which I'm looking right now, he knows more. But um, I think it's a matter of, I mean, you can always propose a scalar field and a potential. Um, and the problem is, as I say, is that this could be say, okay, this is a theory, and then that's it. But then, of course, you have the determination problem in the sense that it could be this or it could be that. I mean, your theory doesn't provide you an explanation of why your theory is the correct one. So maybe if you can, I don't know too much about what exactly the eternal inflationarists are
mm,
proposing in what context, because uh, maybe it comes from, I mean, I know in string theory, for instance, I think this issue has been discussed, but it comes from the bigger project, let's say, of string theory, and not so much of like an independent theory proposal that is about eternal inflation.
okay,
Yeah.
thank you.
Niels.
Yeah, as you know, this week I'm thinking of the methodology for astronomy, especially as a non-experimental science. And I'm just trying to understand how this fits in, if this is a new aspect of how astronomy and cosmology works, or if it connects to previous aspects, right? So some philosophers of astronomy and cosmology focus and say, well, mid-range theories are very important because those we can kind of test on Earth. So in a way, they are experimental, and I guess they're mainly talking about optics or other messengers. But it doesn't seem to be exactly that, right? And I was thinking maybe, I guess it's also not some experiment, really. Is it a Rosetta Stone, as we talked about, in the sense that when you have the long integral, kind of connects these three, the green, the purple, and the other thing, or is it just a completely new method in these sciences that doesn't connect to anything we see elsewhere in this field?
Yeah, I think that's a good question. I'm not sure about it. I feel like, so if we compare it, I mean, I think that well, not a mistake, but the thing that people have mostly focused on is trying to do analogies of a lambda CDM model with a standard particle model, right? Like both are models, and then people think they are similar. But of course, what you say about there is not a lab properly of cosmology has to do with one thing. But I think one of the lessons I wanted to try to point out is that one should maybe study better how lambda CDM model is constructed, because it's not just a theoretical model. It just doesn't come from a full theory. It comes and it's a mixture between, and actually I just put here the simplest way of doing it, but of course then one has to put additional assumption on it. Then usually lambda CDM model proceeds by opening these assumptions a bit and checking if the assumptions are good enough. So I think that the structure of lambda CDM is something at least that has very new properties, right? That I don't feel can be like perfectly compared with other kinds of methodology. So I agree that it includes both, let's say, like a historical point of view, which maybe I have to do more with these phenomenological models, but then it also has to do with the theoretical model. So yeah, I feel like at least one should always start with trying to understand the lambda CDM model, and from that try to do comparisons, and not assuming from the first start that there is oh yeah, cosmology is like from the start like particle physics. It's just a matter of having more data and then we are done. Yeah.
Well, one example that now comes to mind, but that's probably again not exactly what you're saying here, but I wonder how it differs. And so the way Dennis Linkohl thinks of GR, or at least how he interprets the Einstein quote about the left-hand side of the field equations being marble and the right-hand side being low-grade root, right? And then he says, well, that's because GR is a hybrid theory, right? It kind of uses some features of matter, but not all of them. So this feels a bit in the same spirit that you're saying, well, you have this big integral and there are all these features summed over there together. You only take some kind of not collective properties, but overall properties. Is there any connection?
Yeah, but I feel like I'm not sure if I could be convinced that lambda CDM cosmology is a theory. Like lambda CDM model is a theory, right? Like general relativity. So I agree that
okay, maybe it's a hybrid model then instead of a hybrid theory.
Yeah, that's what that is what I think is true. Yeah.
Yeah, sorry if I jump in, but it's very interesting because, in my view, there is a hybrid nature that we can attach, so to speak, or refer to when talking about the lambda CDM, because there is the dark sector that concerns the phenomenological models that also in this slide we can see, and that is also, I mean, problematic in the positive sense because it's a subject of deep investigation. Plus, in my view, we do have as you correctly pointed out, inflation that is to be put outside of this model. We can't reduce the lambda CDM to GR, of course. There is more to lambda CDM. At the same time, we also know that it's not the whole story, and we use inflation in order also to test, paradoxically, we test the lambda CDM through inflation. Hopefully, we will get more information in future missions, even if it's not a very good situation all around the world. I mean, I'm thinking about Lightbird that could have given to us, it could give to us, hopefully, fingers crossed, in the future, more information, just like Lisa on gravitational waves, and therefore we could constrain theories. So we could have, sorry, further constraint to theories of quantum gravity, question mark. And now I come to your point, Antonio. I fully agree with you. I mean, the lambda CDM model is clearly an enterprise, a scientific enterprise that needs both data on the one hand, and on the other hand, theoretical development, even of different, procedures and solutions that can accommodate further data that we will obtain hopefully in the future. Because it's clear that the more theoretical scenarios we do have, the better in terms of the interpretation of the constraint that we will obtain through data. So my question is related, so I have two questions. So the first one is, you quoted from Baumann's 2022 work. As you know, probably Baumann is now working on this positive geometry program. So
Yeah,
are you aware of recent
this
results
one.
that can, or if you want to comment on this? So this is the first question with regard also to the eventually future. How does this positive geometry program situate within the scenario that you described, especially with respect, to the role that inflation should or should not take in the future? And the second question is more related to the dark sector, because do you foresee a change, or do you foresee a modification of your interpretation of inflation in case we obtain, or better, we do not obtain so much information from the dark sector? Because the question is, do you think that the phenomenological models that you call in your schema, right? Do you think that they can play a role in the future in slowly incorporating inflation or not? And if not, why? And if yes, why?
Yeah, no, thank you. These two questions are very amazing because I can relate them very much. So the first one, the Baumann's approach is actually here. It's more or less what I had here when I put this right-hand side picture, this cosmological bootstrap, this idea that one can have a technique of going from, in this case, I mean, obviously these people are thinking in string theory that has all this kind of particles popping out, and in principle they should be in inflation, and from that one can do computations very nicely that then without going into a lot of doesn't need to have a lot of details of what happens in between, but just by symmetries and stuff like this one can show how the outcomes would be. So in the picture here there are these 1 or 2 or 3 or 4. So basically by observing that one can extract what happened in inflation. And actually I used this it was one of the inspirations about how to think about this in terms of this, because as I understand, the whole program actually relies on the fact that it's inflation. So this is a bit more theoretical in the sense that they assume that the background is the zeta space-time, and the zeta space-time has a lot of symmetries. And these are the symmetries that then they use to do this bootstrap. So one can think of in terms of like, okay, in the analog, Bauman does this very nice analogy. They say, well, in particle physics, we have Minkowski spacetime, and there we have a conservation of momenta and conservation of energy, and from that one I can extract already a lot of information. So there's a similar thing here, but the important thing is that this is because de Sitter. Would we have another phase? Would we have radiation dominated? I don't think their program would even go one step because it's highly non-symmetric. And so the point here, actually, and you are right, I think the promising thing here is that indeed they could find something very nicely in these non-Gaussianities, but they rely on inflation. And that's what I think that inflation can have a very nice role in this sense, because in the same way we want to understand baryonic acoustic oscillations and we need dark matter, here we would like to understand this data, we would need inflation. So I see it as very analogous. And then the second question, actually, I had a slide that I didn't add because of time, but maybe I can rescue. So this one I like a lot, because actually from the dark sector, I actually believe it would be the opposite. It will be even worse for inflation for the following reason. So the right hand side is two plots. So there, what this author Gary was analyzing is that, okay, what if now it turns out that we need a new early dark energy model to understand, for example, the Hubble tension, and then the colors there starts from -1, which would be cosmological constant, and then you change this, moving it to try to solve the Hubble tension. So I think the gray line is the Hubble constant measured by the supernova, and the red one is the one that would be measured by the CMB. So changing the dark energy, you can coordinate to put them together. Now, what he shows is that by doing that, you obviously, because of this dynamical intertwine, because dark energy plays a dynamical role in the lambda CDM, you will also change NS and you will also change R. So the initial conditions have to be different to make the lambda CDM works. And now this is terrible for inflation, because inflation, the models are assumed that these parameters are stable. So actually, he proved that it could be possible that for some models, for example, Starobinsky inflation, which is usually the most favored model, and people have a lot of hopes, could actually be disfavored in this sense. So actually, I think, I mean, I feel like this dark energy sector, which is very promising for other parts, for dark energy most likely, actually has in my opinion, it's an obstacle actually for inflation. And this one, yeah.
Yeah, so there are not only, tensions with respect to the Hubble tensions and stuff, but there are tensions that are inside the lambda CDM that
Well, I think for Lambda CDM, that's the whole point I wanted to make. I mean, Lambda CDM doesn't really care what value does NS has. It just fits it. It's a problem for inflation, because inflation obviously wants to say something about NS. But Lambda CDM, like if you don't think about inflation on part of Lambda CDM doesn't care if these are the initial conditions or those, because you don't have a theory of initial conditions.
Yeah, yeah, this is very interesting because it's a sort of, it's very effective. On the other hand, of course, we want definitely to know whether we have to do cosmology or think of the universe, of the early universe, with or without inflation. And therefore, if it's with inflation, then we want to integrate and expand the lambda CDM, including inflation, but at the same time, there is a sort of a circularity because we always need inflation as a term of comparison, unless we don't uh, appeal to approaches that try to avoid inflation. I'm thinking about some quantum cosmology approaches, but I don't think that they succeeded so far in replacing
Mm.
inflation, and also the role that inflation plays for the lambda CDM.
Yeah, 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 yeah. No, no, I agree. Yeah.
Are there other questions from the audience? No? Okay, if not, then we thank our speaker again. It was very nice to host you, Antonio,
Thank
and
you. Thank you
hope to
for the
see you
questions.
soon. Bye all.